some others can join on before we begin, but to those that are on, thank you for joining at this point. Having some more join here and just waiting just a couple minutes here. Okay, I think we'll get started, everybody. Welcome, and I'd like to thank everybody who is spending their time today to join us in our webinar here, Proven Thermal Ceramics for Energy, Carbon, and NOx Reduction. My name is Mike Arbini, and I am the sales director here in North America for Saint-Gobain's Performance Ceramics and Refractories business. If there may be several people not familiar with Saint-Gobain, so I want to kind of give just a little bit of introduction to the company. This is a business that has been in existence for 362 years. That's a very, very long time. The actual start of the company was providing mirrors for the Palace of Versailles in France. So a lot of history with this company. And obviously 362 years, that tends to lead to, yes, there's been a lot of success and proven success. And so Saint-Gobain places, much more success for the future. And as part of that plan, Saint-Gobain has a strategic commitment to reduce carbon or to be carbon neutral by the year 2050. And that includes a couple of intermediate goals. First, to reduce carbon by 20% compared to 2010, and then to reduce carbon additional 33% compared to 2017. So this commitment is really not only for Saint-Gobain's operations, but also for the products and the solutions that we provide to our customers. And that is really why we are here today. It is a portion of what we want to promote, what is being proven now in the marketplace. And I think everybody, any company, business these days, sustainability, carbon neutrality, energy reduction, it's all part of our global being now. And it's important of what we're trying to convey today and what we're promoting to our customers and proving to our customers today. The products and solutions that we will be talking about, there'll be several topics within the presentations today, but we'll touch on additive manufacturing of advanced silicon carbide parts. We'll talk about advanced thermal designs, computational modeling and testing, and laboratory and field validation, including data monitoring. And I think this is what's going to be very important, is what we do in regards to computation and in the lab is being proven out in the field. Very important, and we'll touch on that today. I am joined by two colleagues today that will present. The first one is Tom Brizzledon. He is our Director of Business Development. Tom is actually the person that invented the product and technology and developed it. And he's key to our moving forward with this technology in the market and the success that we've had today. The second person that will be talking today is Dr. Brad Nakanishi. He is a senior research engineer, very much in depth in this technology, the testing, and he'll go into some of the research and the theoretical that we've developed that has been proven in the field. Before we get started, just a couple of housekeeping notes. It would be great if everybody can hold their questions until after the presentations. We will go into a question and answer mode, and then you will see, those questions being popped up onto the screen. I will say that the questions are anonymous to the entire group. It's only the presenters that can see the names of the questions. So again, feel free and don't be shy and ask what you'd like to ask. So with that, I think we'll turn this over to Tom Brizzleton first, and he'll get started on the initial burner solutions concept.
Great. Well, thanks, Mike. Thank you for the introduction. And thank you, everyone, for attending today's webinar on proven energy, carbon, and NOx reduction with innovative burner solutions. Looks like we have a very international crowd, and so it'll be a great event to exchange. So let's look at the focus. Mike kind of gave you an overview of Saint-Gobain. Today, our focus is on enhancing radiant tube combustion systems and continuous galvanizing and annealing lines. Where we're interested in reducing fuel, carbon, and NOx to help companies meet their near-term 2030 and long-term 2050 sustainability goals. To help foster near-term implementation with excellent ROIs, solutions will be discussed that are retrofit in nature and require a total solution, including advanced thermal designs, computational modeling, and testing. A further goal of these designs is to have minimum impact on the burner and control system. I'll discuss shortly additive manufacturing of twisted tapes, twisted channels, and flame-splitting inserts that meet the goals earlier stated. Dr. Brad Nakanishi will show you how these are optimized using computational modeling and testing. And then Mr. Yoon-Sik Jun would normally give the presentation. He's from POSCO. However, due to he's unavailable for this presentation, so I will go through his presentation. While the focus today is on radiant tube combustion systems, the methods described are applicable to direct freight burners as well. So while radiant tubes are generally small when compared to something like a blast furnace, both individually and when combined, their impact on energy, carbon, and NOx can be significant. A single radiant tube will typically use 85,000 cubic meters of natural gas a year, generate 150 metric tons of carbon and 256 kilograms of NOx. If we apply a total solution where we reduce the energy by, say, 20% and NOx by 15%, the NOx is pretty impressive when we apply it to, say, only 5,000 radiant tubes. The reduction will be on the order of 880 gigawatt hours of natural gas, 150 kilotons of carbon, and a half kiloton of NOx. And all this can be done while using very simple, like I said, retrofit technology. The enabling platform that makes these designs possible is really the ability to additively manufacture advanced silicon carbide. Includes both traditional 3D printing of complex shapes and the use of a unique powder extrusion to make large format designs for industrial applications. In some cases, the material will be joined to more traditional materials such as reaction bonded silicon carbide and alpha bonded silicon carbide. In order to achieve the energy, carbon, and NOx reduction goals, the material plays a critical role in allowing these designs to operate effectively in extreme environments, namely high temperature to meet all applications, thin walls, high thermal conductivity and emissivity for excellent heat transfer. A non-porous, low oxidation material matrix is required. When we combine these components, they significantly reduce thermal shock, resulting in really a perfect material for long life and combustion environments, using both natural gas and coke oven gas. 3D printing allows us to move to advanced thermal designs that cannot be made with traditional methods of slip casting, pressed, extruded, and even injection molded. So it really gives us a method for customizing our technology specific to a given application. So let's just zero in on the radiant tube itself. We want uniform heat transfer from the tube to the steel, minimum energy use, CO, CO2, and NOx generation, preferably less than a 2-year return on investment or payback. In a report generated by the Department of Energy, they identified the theoretical practical reduction of energy as going from about a gigajoule per ton to about 0.65. This corresponds to a CO2 reduction per ton from about 53 to 34 kilograms. And then the South Coast Air Quality Management District, which really seems to be the most stringent in the U.S., is targeting less than 40 ppm of NOx for industrial heating processes. So with all this in mind, we want to enhance the radiant tube heat transfer, improve the heat exchanger effectiveness, and simultaneously reduce NOx. Kind of sounds trivial, but several of these statements are contradictory. As an example, increased efficiency can require higher levels of preheat air, which, if not managed properly, can increase NOx. The unique issue with enhancing the radiant tube heat transfer is that the burner leg utilizes both convection and radiant heat transfer from the flame. When the combustion process is complete in the third and fourth legs, the exhaust gas loses nearly all of its radiative properties. Thus, convection is the primary means of heat transfer and is lower than that of the combined. So how do we make the exhaust leg look like the burner leg? The use of spiral twisted tape inserts provides an effective means when combined with additive manufacturing to make a device that absorbs exhaust energy and re-radiates similar to the flame. Interestingly, we find that a ratio of the surface area of the tube to that of the twisted tape being approximately 1 gives the ideal balance of radiation and convection in the exhaust leg. Additive manufacturing, as compared to slip casting or injection molding, allows the twist rate to be easily modified and optimized for a given radiant tube. While increasing the twist rate further enhances the heat transfer, overheating may occur. However, this may be an advantage, in example, in a radiant tube made of ceramic. Typically, 3 to 18% energy and CO2 reductions occur with minimal pressure drop, usually on the order of about 0.01 to probably a maximum of 0.8 kPa. So moving on beyond the twisted tape or the spiral core, let's take a look at how the heat exchanger can enhance our system. So the effectiveness of the heat exchanger or recuperator is driven by the overall heat transfer coefficient and surface area. The temperature tends to be fixed by the application. Recuperators are designed as simple straight tubes or enhanced with fins or bumps. With this design in a parallel flow heat exchanger design, overall system efficiencies are typically between 60 to as high as 68%. Enhancing this design needs to address both improvement to surface area and the heat transfer coefficient in order to minimize pressure drop. So here's how we do that. Extending the concept of the twisted tape to that of a heat exchanger, a twisted channel is shown to be an effective means of increasing both surface area and overall heat transfer coefficient simultaneously. The twisted channel imparts a velocity vector perpendicular to the heat transfer surface area that almost acts like a jet. This increases the Nusselt number and the overall heat transfer coefficient by about 25%, as shown in this diagram on the left. Increasing the surface area with the assistance of additive manufacturing allows for a significant change in surface area as compared to fins and bumps. A typical recuperator will have a surface area of, let's say, 450. A shallow 3-fin twist design can match this surface area. However, when increasing both the number of twisted channels and the twist rate, a surface area of 2 times is achieved. The corresponding improvement in heat transfer coefficient allows overall radiant tube efficiencies to approach 85%. Thus, 5 to 30% energy and carbon reductions can be realized. The combined reduction of flow rate and improved heat transfer coefficient and counterflow designs allows pressure drop to be minimized in the overall system. And as I mentioned earlier, there is a potential to increase NOx, and so we needed to come up with a solution to reduce NOx. So now we're introducing the NOx Buster. So originally, the NOx Buster was based on an internal exhaust gas recirculation system. Some of you may have seen, external EGR systems, selective catalytic reduction systems. This is actually a simple device that's placed inside the radiant tube within the combustion process. So originally, when we were focused on exhaust gas recirculation, we saw 35 to 50% NOx reduction. However, it was limited to a select number of burners with relatively high velocity at the burner exit. Addition of nozzles to low velocity burners changed the burner, so we really weren't satisfied with this. And so now here you can see we place a NOx Buster downstream of the burner, so there's no impact on the burner or the control system. And through computational modeling, we've optimized what we call a flame stretching concept, where, again, it has minimal impact to the burner control system. By applying this design combined with computational modeling, we approach NOx reductions of 70%. And so now Dr. Nakanishi will further expand on this concept and the optimization of our total solution that combines improved radiant tube heat transfer with twisted tape spiral core inserts, increased heat exchanger effectiveness with twisted channel heat core, and then the NOx reducing flame splitting device, the NOx Buster.
Thank you, Tom. Appreciate that. And again, I will reintroduce Dr. Brad Nakanishi, and he will really go into the lab to field type of results. And go ahead and you can take it, Brad.
All right. Thank you, Mike. Hello, everyone. Thank you for joining us for this exciting discussion today. Please feel free to share any of your questions with us in the Q&A following our discussion here. So my section will come in 2 parts. First, I'm going to review the benefits and challenges for improving combustion heating efficiency and emissions. Then I'll show how we can realize this using the POSCO Saint-Gobain collaboration as a case study. Improving combustion heating efficiency helps to reduce energy consumption or increase product throughput, or some combination of the two, depending on process conditions. To illustrate what I mean by this, consider the 3 Sankey diagrams shown here, illustrating the energy flows in a recuperated furnace. This furnace could be a continuous annealing line utilizing radiant tube heating, or really any indirectly or directly fired heating process with recuperation. The left diagram shows energy flows for a conventional metal plug recuperated system. Here, energy inputs, fuel, air, and their mutual combustion heat are assigned 100 arbitrary energy units. And heat flowing to the load, for example, that could be the steel strip, the exhaust, as well as any leaks in the furnace are also shown. On the right, consider 2 extremes for a system utilizing high efficiency ceramic inserts and recuperators. The top furnace operates at similar throughput to the conventional system on the left, but here 18% energy savings are realized. Similarly, the bottom furnace operates at similar energy input while adding 22% to the throughput. Real systems likely operate with some mix or combination of these two things. We'll focus on energy savings in the remainder of this talk, but the key point I want you to take away from here is that energy savings and throughput are related benefits of higher heating efficiency. And in terms of specific CO2 emissions measured in ton CO2 per ton product, which is proportional to the ratio of input and load energies, any combination of energy savings and throughput with a higher efficiency system reduces the specific CO2 emissions, and in this case, by 18%. The two main challenges for improving the efficiency of recuperated combustion heating systems are pressure and NOx. Here, I schematically show how pressure, that is the pressure drop across the blower to the exhaust stack for a radiant tube or a radiant tube furnace zone, the recuperator surface area, as well as NOx emissions and preheat air temperature vary with energy savings or energy efficiency. On the left, as energy savings is increased, the recuperator surface area increases, which in turn increases the pressure drop of the overall combustion system. Typically, blower systems operate at low pressure, and upgrading adds additional costs. Fortunately, twisted channel recuperators may be optimized using computational modeling to minimize pressure drop and avoid blower upgrades while providing additional energy savings. On the right, reducing energy consumption by recuperation increases the preheated combustion air temperature. Because NOx is a thermally activated process, you will likely find significant increases in NOx at higher flame temperatures while targeting additional energy savings. Fortunately, as Tom will show, and I will show through some lab scale studies, that this may be avoided by utilizing ceramic inserts to reduce NOx by up to 70%. To illustrate the benefits and challenges in action, I'll share how Saint-Gobain assisted POSCO to deliver a solution that saves 24% on energy consumption while reducing NOx emissions by 15% in a field installation. In the interest of time, I won't dive into details here, but please feel free to post any of your questions on this in the Q&A. Results from a series of trials at RIST, a research affiliate of POSCO, and POSCO are shown on the left. The baseline system consists of a W-tube burner, an EGR system or external gas recirculation system, and a metal plug recuperator. The remaining trials utilize various configurations of heat core, NOx buster, and spirocore as illustrated in the bottom figure. Leveraging Saint-Gobain's pilot scale test furnace and previous experience with heat core and spirocore, the designs may be optimized with modeling and rapidly manufactured to achieve the targeted performance. Notice in trial A, that is using heat core version 1 without a NOx buster, provides 16% energy savings while increasing NOx by more than 40%. This is a direct result of the higher combustion air preheating while using the heat core. To combat higher NOx, the NOx buster, a ceramic insert positioned downstream from the burner in the flame, reduces peak temperatures and NOx, as you see in these figures on the right. After a few iterations of testing at RIST with modeling input from Saint-Gobain, we created a NOx buster that reduces NOx below POSCO's targets while maintaining the significant energy savings with heat core. Finally, I'd like to highlight how we solved a critical problem that we encountered during the field trial at POSCO involving soot formation. Shortly after POSCO restarted their furnace, now installed with the tonal burner solutions in a single zone, POSCO observed some strange behavior that ultimately required a zone shutdown and further investigation. After removing the burners, they discovered significant soot deposits on the NOx busters in multiple radiant tubes. This was not a great situation for POSCO. However, long story short, Saint-Gobain's R&D teams were able to reproduce POSCO's conditions using our own pilot furnace at our R&D center in Paris, and then we conducted a series of tests and simulations to determine the root cause of the soot and develop a viable solution for POSCO. Together, POSCO and Saint-Gobain learned that managing the NOx buster position during the installation is very critical to prevent soot formation. And more importantly, we obtained a good solution that simplified the installation process for POSCO while having little to no impact on their furnace operations. So with that, I'd like to thank you for your attention. And of course, I encourage you to post any of your questions to the Q&A following our presentation. It's been my pleasure to share these exciting results with you. And I'm now going to pass it back to Tom, who's going to tell you more about the field trial at POSCO. Thank you.
Thank you, Brad. And as Tom mentioned at the beginning of his original talk, we typically have a POSCO representative from Korea with us that presents this portion. Obviously, we have done some very significant things within POSCO, and their appreciation has been to support us and to show what our products are capable of. Unfortunately, it is in the middle of the night, and Yunsik could not be with us, but Tom certainly is well aware of our work at POSCO. He's been very involved, and he can give this presentation, which he will at this point.
So thanks, Mike. And yes, I'll be speaking on behalf of Yunsik Jun. He is the team leader of the energy department at the POSCO Pohon Works. And really his goal is to reduce energy and CO2 emissions along with NOx. And so this part of the presentation is really two parts: a laboratory evaluation that POSCO did, and then followed up with a field validation specifically focused on energy and carbon and NOx reduction. We've been working with POSCO on this for since 2018. Some pretty impressive numbers here. The Pohon Steelworks consumes about $100 million of natural gas in reheating and annealing, in their reheat and annealing lines. And therefore, in today's world of sustainability, reduced carbon, it's critical that they reduce energy and CO2 emissions. The silicon steel plant in Pohon Steelworks has about 495 radiant tube burners, using, again, 82 million cubic meters of natural gas. The furnace runs about between 950 to 1,050 degrees Celsius, which is really, from my experience, pretty much on the extreme end of the lines such as this. So there was a strong motivation to apply new technology, new innovative technology to save energy and reduce CO2 and NOx emissions. So they really moved in two steps. The first step was to apply the spiral core technology that was earlier introduced, and then following the spiral core technology, apply the heat core technology to replace the existing recuperator. And then finally from this, because they did, as Brad showed, increase NOx, we installed the NOx buster technology in the system. So looking at graph 1, spiral core produced an increase in the temperature of the radiant tube, which we expect. This allows more energy to be transferred into the furnace, limiting the amount of energy going out the exhaust. When we look at graph 2, taking a closer look at the fourth leg temperature, a 25 degrees C increase is observed. Then just kind of looking at the heat core. The heat core uses a counterflow design in this application to obtain the maximum temperature differential and heat transfer. Where a lot of heat exchangers are parallel flow, the counterflow really allows us to capture the maximum benefit of the heat core technology using the twisted channel. So the spiral core is, as earlier discussed, a twisted tape. In the laboratory trial, they saw a 5% fuel savings. And this was at temperatures between 900, 950 degrees Celsius. The system that was used was 6 elements. However, the field test was actually performed at 950 to 1050 degrees Celsius. But again, looking at the lab test, they optimized the combustion air ratio from between 1.1 to 1.2. And they also did examine 2 types of inserts, the Saint-Gobain product, the spiral core, and then what we would consider a competitive technology. Just through the laboratory evaluation and the energy savings they saw, they selected the spiral core. They also did some computational modeling in the radiant tube, and through that also found similar energy savings of 5%. So then after the spiral core laboratory trial, they looked at the recuperator. So as we discussed earlier, the recuperator is a 3D printed technology, additively manufactured. And however, the laboratory trial showed an 11.5% fuel savings. So we had actually significant discussions on, how to both improve the fuel savings and then reduce the NOx. And so then later on, after the trial, we did install the NOx buster on the burner side of the radiant tube. So combining the recuperator and the NOx buster generated the results that POSCO was interested in. So then the combination of the technologies, and now this is in the lab. So the combination of the spiral core, the radiant tube insert, and the recuperator showed a fuel savings of 16.5%. And also then the increase in the radiant tube temperature, which allows more energy to be transferred into the furnace. The next step now was to go into the field. So they installed 68 sets of spiral core, the radiant tube inserts, into their annealing furnace. And from this field trial, they saw a 7.9% energy savings. So pretty unique. They saw about 5% in the laboratory and then 7.9% when they actually applied these into the field. And down here, you can see typical installation. They both tried 5 elements and 4 elements, and then the installation of the spiral core in the furnace. And this shows the test results from different trials. And again, this would be the use of the heat core in the radiant tube furnace, and here just with the heat core they saw 15.3%, and this was done about a year and a half ago. They installed 10 sets of the heat core. So now looking towards the field. So in the laboratory test results, they saw 16.5%. When they applied both the spiral core and the heat core in the field, the overall energy savings was 23.2%. And so now the next event is to install 58 sets of the recuperator NOx buster to complete the furnace. And then they're anticipating a second furnace to be installed later this year or in the final year. And so with that, again, so this concludes our presentation. We thank everybody for attending today, and we look forward to questions and answers. And so I'll turn it over to Mike here for a little bit.
Thank you, Tom. I just turned on the Q&A mode, so anybody that would like to ask a question, please feel free to type that in, and we'll bring them up as required. Or if not, we will maybe go into some questions too.
Will we be? I think I saw it right here.
There we go.
We'll be posting the presentation. I think the presentation, it's either a YouTube mic or it's posted on our website.
Yep. Okay, so the first question: do you have the amount of money that was saved at POSCO?
That's a really good question. So I don't have it right at the tip of my tongue, but 23% 23% energy savings on the number of radiant tubes. I'd have to calculate that, and then we could apply that to the I don't know, he was saying 80 million cubic meters of natural gas. We don't know it's significant.
Thank you. A typical question, Tom, that comes up in some of the other webinars has been lifetime of not only spiral core, but ceramics in general. Can you expand on that?
So the spiral core, when applied in a radiant tube, it will outlive the life of the radiant tube. And then our customers really have two choices. As they see the radiant tube failing, which usually occurs between 3 to 5 years, they have removed the spiral core, put in new tubes, replaced the spiral core. We've had customers successfully do that for anywhere between 2 and 3 tube changes. If the tube does fail, a lot of times it'll capture the spiral core, and sometimes you can't recover it, but sometimes you can. But we've had spiral core in operation in this environment for over 10 years now.
Thank you. We have another question here. So were these tests performed on, I'm sure you're reading that, right, Tom?
Yeah, were these tests performed on ceramic, SiC radiant tubes, or alloy? And did this affect the life of the radiant tube? So most of the applications where we've applied the spiral core and even the heat core technology have been on metallic radiant tubes or alloy radiant tubes, high nickel chrome alloys. And that's really our primary focus. Now, there have been some early developments in using spiral core in ceramic U-tubes. To my knowledge, there's only about 10 of those out in the world. But they work in either system. So they work in both metallic radiant tubes as well as ceramic radiant tubes. And we have applied similar technology in, most of the ceramic radiant tubes are single-ended. So we have applied the heat core technology and what I would call a modified spiral core. We actually call it a pyro core in single-ended radiant tubes that use ceramic outer radiant tubes, ceramic inner, and ceramic recuperators.
So Tom, maybe you can expand a little bit, because this question comes up a lot about temperature capability of our products versus alloys.
Yeah. So our the working temperature of the material is 1350 degrees Celsius. Most alloy radiant tubes that I know of operate, in that the temperature range of 1000 C, maybe as high as 1150 C. So the silicon carbide material is actually perfectly matched for this application.
Another question?
Yeah. I'm not sure I can say double, but we definitely have an impact on improving the tube life. So let me read it. Can we double the lifetime of a metal radiant tube using spiral core? I'm not sure I could say double, But really, two things happen: the improved temperature uniformity that the spiral core provides. It can help improve, the thermal expansion differential in the radiant tube, and that can help increase the life. The other thing, that applying the spiral core does is you do use less natural gas, so the burner in the burner leg isn't firing as much, and it can help extend. Really, where the radiant tube fails the most is that burner leg, and so it can help reduce that. But I'd be stretched to say that we could double the life.
And maybe you can expand a little bit, Tom, too, on our success in the different types of radiant tubes, straight, U, W, and where we are not participating right now.
Yeah. So the spiral core has been applied in straight radiant tubes. It's been applied in U tubes and W tubes with actually very, very good success. W tubes typically have an energy savings on the order of about 5%. U tubes are about 10 to 12%. And then in straight tubes, just because of the base efficiency of that technology, we can see anywhere between 15 and 20% energy savings.
Perfect. It's a question that comes up a lot in regards to the different types of tubes that are out there. Next question: how do we decide recuperator's length?
Yeah, I probably should turn this one over to Brad. Brad hasn't talked, but Brad's the optimization guy. So let's turn this one over to Brad.
Sure. So as I mentioned, kind of the two design parameters that we look at with customers are the energy savings target and the pressure drop. And so, in terms of determining things like the recuperator's length or the heat core's length, and some of the other factors like the diameter, the twist rate, and these kinds of design parameters that we really try to look at what is the optimal heat core design or length that will give the required or targeted energy savings, whether it be 10, 15, 20, 25%, while also managing the pressure drop in the system so that it's compatible with kind of the existing infrastructure at the customer site. Thank you.
Okay, I again would like to expand on one other topic, Tom, if you could touch on too, is how we approach direct fired burners and how the technology comes into play there.
Yeah. So the early system, we use the heat core as part of a self-recuperative combustion system. So depending on your application, it's feasible that we can apply a heat core in replace of the existing recuperator on a direct fired burner. I think also the NOx buster has a very high potential to be applied in direct fired burners. As we're finding, and maybe Brad can expand on this a little bit, we're finding that the NOx buster technology really impacts the flame characteristics, which are actually similar in a variety of different burners, whether it be nozzle mix, partial premix, air stage, or gas stage combustion. And so maybe, Brad, you can expand a little bit on that one.
Yeah,
Don't mean to put you on the spot.
Yeah, I mean, I guess all I'll add there is just as we've tested the NOx buster with different burners, different size radiant tubes and things, our knowledge of how this device is working and operating is improving and increasing every day. And so, yeah, I think we'd be really excited, if you're interested in this product, to be able to work with you and take a look at, what system that you're utilizing and be able to get you a great solution for, meeting whatever NOx requirements that you're looking for.
This is a great question. Is there a situation where the use of only one of the mentioned technologies is recommended? Example, only NOx buster. So we promote this as total burner solutions. But, as Brad alluded to a little bit, we really want to see what is the driver at the customer site. If the focus is NOx, we can apply the NOx buster. If the focus is energy, we can apply only the heat core or the spiral core. If the focus is on throughput, then we apply the spiral core technology. And so really it's really what is best for a given application. And then of course, what is the value proposition? So in NOx, it's usually penalty avoidance, carbon and energy reduction. We have carbon credits, and then also the value of energy. And then usually the biggest one, although it's harder to quantify, is the improvement on throughput. But again, our goal is to do what's best for the customer, and if NOx is what you need, that's what we'll focus on. And the beauty of these technologies is we can apply one or multiple technologies as is needed. And then the other thing I would say is later on, like if we focus on NOx and now energy becomes an issue, the systems add on to each other. So, we could apply a NOx buster and then add a heat core, or we could apply a spiral core and then add on a heat core at a later date.
And it should be noted when we begin our conversations and engagement with customers, we will, go through in detail what really is the pain points, what the customer is looking for, and that includes a very detailed payback analysis for our offer. So no matter what we do out there, whether it's just spiral core or a combination of things that Tom just discussed, we will include a payback analysis as part of that offer.
I see another question, Mike.
Yep. Sorry about that.
There you go. What is your solution for single-ended radiant tubes? The several technologies can be applied to single-ended radiant tubes. The one that's probably of most interest, it's like a modified spiral core. So we take a spiral core, increase the inside diameter of the tube, and then in essence we replace the flame tubes inside the single-ended radiant tube to enhance the heat transfer. And really what it does, because we can, through additive manufacturing, we can vary the twist rate of this insert. We call it a pyrocore. And by varying the twist rate, we can come up with very uniform temperatures on the radiant tube. And we've seen this is important in a lot of heat treating applications, in whether it's carburizing, whether it's hot stamping, where it's very critical to have a uniform heating of the material. So that's the first technology. The second technology that we can apply, assuming the burner is amenable to it, is to apply the heat core in replacement of the recuperator. And so that would increase the efficiency of the system. And there are actually some burner companies who have adopted that technology into their burners. And then finally, depending on your single-ended radiant tube, if you have metal radiant tubes or even ceramic radiant tubes, Saint-Gobain does offer ceramic radiant tubes up to, well, actually as small as I think like 100 millimeters by, let's say, a meter long, to as large as 300 millimeters by 3 meters long.
Not sure there are any more questions at this point. It looks like that might be the end. Certainly, if somebody wants to ask another question, please pop it up. But if that is it, again, I would like to thank everybody for their attendance today and your time again. We're very excited about this technology and the sustainability aspect of it. And it is being proven in the field, and we're getting much more attention now as we move into a different era of saying a greener planet. So we're very excited about the product and technology, and we ask you to please contact us to learn more about the product and have one of our application engineers to drop in. We're globally located and have everybody out in the field from Asia to North America to Europe. Will certainly be amenable to coming into your facility and discussing more of this. Looks like another question came up.
I'll say maybe I could take this one, Tom. So it says, does Saint-Gobain have any laboratory to test solutions to the potential customers, or the customers have to ask for the materials and make the test by themselves? So I think long and short is yes. We can work with customers in either respect. We have testing capabilities at our R&D site, as I mentioned in the presentation, at our R&D facility in Paris. We have a full 1-to-1 scale radiant tube test furnace at that site. And we're also happy to work with, directly with the customer on the testing side if that's their preference. But it depends on the circumstances, and happy to work with you.
Very good. Thanks, Brad.
Mm-hmm.
Well, I know we're a little early, but again, I'd like to say thank you to everybody. Please reach out to us. We're easily found on the internet and through this platform also. So hoping to hear from some of you and to discuss this a little more detail at your own facility and see what we can do to provide solutions for your specific need. So thank you, everybody. And thank you, Tom and Brad.
Thanks,
Thank you, everybody.
Take care.
Bye-bye.